Welcome. I'm sure you've all heard of masers and lasers. Maser is an acronym for microwave amplification by stimulated emission of radiation, and laser stands for light amplification by stimulated emission of radiation. Perhaps you have not seen a maser, but I'm sure all of you have seen a laser. Perhaps you even own one, the laser pointers that you use when you give a lecture. Today I'm going to tell you about masers in the sky, celestial masers. Yes, long before we invented the maser and laser, nature has been blazing away or mazing away. But before I tell you about that, we have to set the scene. And our story begins in 1917 when Einstein published one of his most famous papers on the quantum theory of radiation. In that paper, he introduced the important notion of stimulated emission of radiation. People knew that an atom or a molecule can spontaneously jump from a higher energy level to a lower energy level, thereby emitting radiation. But this was the notion of stimulated emission, radiation which is stimulated by an incident radiation field. So let's try to understand what Einstein was trying to tell us. The opening sentence of his paper is very interesting. The formal similarity of the spectral distribution curve of temperature radiation, black body radiation, and Maxwell's velocity distribution curve is too striking to have remained hidden for very long. Here is the spectrum of black body radiation, intensity as a function of wavelength or frequency. And what you have on the right is the distribution of the speeds of molecules or atoms in a gas at a certain temperature. Einstein was pointing to the similarity between these two and the hidden message in that similarity. In this fundamental paper, as I said, Einstein introduced the idea of stimulated emission of radiation. To explain that, let us consider a two-level atom or a two-level molecule in an external radiation field U of nu. I've shown you two energy levels, N and M. Later on, I'll call them 1 and 2. And there are three processes at work. One is, of course, stimulated absorption. An incident photon makes an atom or a molecule make a transition from a lower energy level to upper energy level. And an atom can jump from an upper energy level to a lower energy level, emitting a photon. But the new idea was one of stimulated emission. An atom or a molecule, which is in an excited state, the state M in this diagram, can be tickled to jump to the lower level and emit a photon. It can be tickled by an incident radiation field. That is the notion of stimulated emission. Now let's write down the rate of transition from the state M to N, from the upper level to the lower level. There are clearly two processes involved. One is the spontaneous emission, which Einstein said is proportional to a coefficient A, which is independent of the external radiation field because this is spontaneous emission. And there is a second term, which is C into U nu, where C is a coefficient which is associated with stimulated emission. And of course, both these terms have to be multiplied by N of M, which is the number of atoms or molecules in the upper level M. And U nu is, of course, the incident radiation field. Now, you can also have a transition from the lower level N to the upper level. And that, Einstein said, is governed by a coefficient B. And of course, the rate, the number of transition per unit time, will be given by B multiplied by U of nu, which is the incident radiation field at a particular frequency nu, which is the frequency is the energy level difference divided by Planck's constant. And n of n is the number of atoms or molecules in the lower level n. So this is the rate of jumping from the upper level to lower level, and this is the rate of going from the lower level to the upper level. In thermodynamic equilibrium, these two rates have to be equal. The number going up must be precisely equal to the number coming down. So I have taken these two equations from the previous slide. A plus C U nu, number of atoms in the state M, must be equal to B U nu, number of atoms in the lower state N. Now you can solve this equation for U of nu. And an elementary shuffling of terms will give you U of nu is given by A over B divided by the number of atoms in the lower state divided by the number of atoms in the upper state minus C over B. So this is the radiation field. We have solved for the radiation field. Now, in thermodynamic equilibrium, the ratio of the number of atoms or molecules in the level N divided by the number of atoms or molecules in the level M is given by e to the power minus the energy level difference divided by kT, which can be written as e to the power h bar omega over kT, or h nu divided by kT, and that's what Bohr taught us way back in 1913. Therefore, the radiation field must be equal to A over B, and for this ratio in the denominator, I've written e to the power h bar omega over kT, or e to the power h nu over kT minus C over B. So this is the radiation field. Now, what Einstein did was to use this condition of thermal equilibrium and say that in thermal equilibrium, when matter and radiation are in equilibrium with one another, not only the various energy levels are in equilibrium, but matter and radiation are also in equilibrium. We know that in that case, the radiation intensity as a function of frequency must be given by Planck's law. 8h nu cubed by c cubed multiplied by 1 over e to the power h nu over kT minus 1. So that's what it ought to be. Now that tells me immediately that this ratio A over B must be equal to 8h nu cubed divided by c cubed. It also tells me that the ratio of C over B must be equal to 1. So let me summarize and tell you what Einstein did in this paper. He said, look, there is also stimulated emission. It is the interplay between spontaneous emission, stimulated emission, and stimulated absorption that gives you Planck's law. So this, in a sense, was a derivation of Planck's law. Therefore, in order for Planck's law to obtain, not only you must have these three coefficients, but these coefficients must be related to one another according to these two relations. Now, if there is no stimulated emission, this new idea, if it wasn't there, then C is equal to 0. Therefore, the second term in the denominator doesn't exist. And A over B is given by 8h nu cubed divided by c cubed, and U of nu is given by 8h nu cubed by c cubed multiplied by e to the power minus h nu over kT, which you will recognize is Wien's law. In what regime does Wien's law obtain? If you go to Planck's distribution and ask, what is the approximate version of this Planck's distribution when h nu is very much greater than kT, then you can neglect the second term in the denominator and take this upstairs, and you will get e to the power minus h nu over kt. So when h nu is very much greater than kt, Wien's law must obtain. Please also remember, when h nu is much greater than kt, that means the energy level difference is very large. That means most of the atoms or molecules will be in the lower level. Very few will exist in the upper level, and therefore stimulated emission is not that important. Spontaneous emission will take place, but stimulated emission is proportional to the number in the upper level, and therefore stimulated emission is not important. That corresponds to C being equal to 0. What Einstein noted in this famous paper is that if he didn't introduce stimulated emission, then he could only get Wien's law, whereas what he wanted to get was Planck's law, because that is the correct distribution of the energy density if matter and radiation are in equilibrium. In order to get this Planck's law, he had to introduce the notion of stimulated emission of radiation. So the profound insight of this paper was this: whenever there is spontaneous emission, there must be stimulated emission. And whenever there is stimulated emission, there must be spontaneous emission. It was this very deep principle that led the great Russian physicist Zeldovich in 1972 to advance the notion that even non-rotating black holes must radiate. And he posed this question to Stephen Hawking. And as I discussed in the earlier lectures on black holes, in 1974, Hawking showed that a non-rotating black hole, a Schwarzschild black hole, does indeed spontaneously emit particles and radiation. Now, let us make the connection between Einstein's coefficients and quantum mechanics. Please remember Kirchhoff's law. What Kirchhoff stated in 1859 is that the ratio of the emission coefficient to absorption coefficient, go back to lecture number 2, and you must revise that, because I'm going to pick up from lecture 2 from this point onwards. The ratio of emission coefficient to absorption coefficient is the radiation intensity B nu of T. If the body is opaque, this B nu of T is given by a universal function of temperature and temperature alone, which is Planck's radiation formula. Now, this relates to emission and absorption for a thermal emitter. Clearly, there must be some relation at the microscopic level also, because in our second lecture, we merely characterized a macroscopic substance with an emission coefficient J nu and an absorption coefficient alpha nu. We didn't say where these things come from. As I said, it's like we introduced the notion of a dielectric constant, a refractive index. Classical physics doesn't tell you where these properties derive from. That is in the realm of quantum physics, and that's what Einstein was trying to do. Now I'm going to change notation from n and m to 1 and 2 because it's more logical. And let us say there is a level 1 and 2, the statistical weights are G1 and G2, and their energies are E, and the second level has a higher energy, E plus h nu, or the difference in energy is h nu. Very good, let's proceed. According to quantum theory of radiation, the spontaneous emission coefficient A21 that Einstein introduced, Einstein simply introduced it as a coefficient. He didn't know in 1917 where this came from or how to derive this. That had to wait till we had the full quantum mechanics. And what quantum mechanics tells you is that A21 is the transition probability per unit time for spontaneous emission. In quantum mechanics, please remember, nothing is stated with certainty. You can only give a probabilistic distribution for absorption or emission or scattering or anything you like. So Einstein's A coefficient is related to the transition probability, spontaneous transition probability from level 2 to 1 and per unit time. Now let us look at stimulated absorption. An incident photon h nu makes an atom or a molecule jump from lower level 1 to upper level 2. The probability, once again you have to talk in terms of probability and not certainty. The probability per unit time for this absorption will be proportional to the density of photons at the frequency nu. Clearly, if there are more photons at the frequency nu, the probability will be larger. And what quantum mechanics tells you is that the B12 that Einstein introduced, the coefficient B12 of going from level 1 to level 2, is given by the transition probability per unit time for the absorption from state 1 to state 2. And since this probability is obviously to be related to the intensity of the incident radiation at the frequency nu. Now, please remember that although I draw E1 and E2 as sharp energies, these energies are never sharp unless it is the lowest energy level. There are various reasons why the energy levels are not sharp. And if they are not sharp, when an atom or a molecule jumps from upper level to lower level, it will not emit precisely the frequency nu such that h nu is equal to E2 minus E1. Because E2 is slightly fuzzy and E1 may also be slightly fuzzy unless it is a ground state, the line that is emitted or the line which corresponds to absorption, here I've shown you an emission line, will have a certain width. And emission at any particular frequency will be related to the transition probability at that frequency. Since the total probability always has to be 1, the integral of this line profile over the frequency nu has to be equal to 1. Now, why does the line have to have a width? Why should the energy levels have to have a width? There are many possible reasons. One is the uncertainty principle itself tells you in a finite time you cannot measure the energy of a level to infinite precision. That comes from Heisenberg's uncertainty relation. Here the conjugate variables are energy and time of observation. Secondly, the atoms or molecules may be moving. Therefore, there is Doppler broadening. Thirdly, there is also pressure broadening. If the gas is at a certain temperature, it has a certain pressure, which is nKT, and the pressure also leads to broadening. If you have not read about these things, I suggest you pick up some introductory book on modern physics like Rittmeyer and Kennard and Lauritsen or Feynman lectures and read about the various reasons why an absorption line or an emission line has to have a certain width. You can't get away without it. Now let's go to stimulated emission. According to quantum mechanics, remember we are in 1917, quantum mechanics still didn't exist. It came at the end of the 1920s. But quantum mechanics relates stimulated emission to the transition probability per unit time from level 2 to level 1 induced by the incident radiation, and that is equal to B21 multiplied by U of nu. Now, without stimulated emission, let me repeat once again, Einstein could only get Wien's law. He could not get Planck's law. So he had to introduce the notion of stimulated emission. And it is this interplay between stimulated emission, spontaneous emission, and stimulated absorption that gives rise to Planck's law. Now let's pursue this story a little further. Here are two energy levels 1 and 2. There is stimulated emission and there is spontaneous emission. Now this is the most important thing that you must remember, which is relevant for today's lecture. stimulated emission, this stimulated emission takes place in the same direction as the incident radiation. Now, if you have 10 to the power 23 atoms or molecules in the upper state, and they are undisturbed, and they spontaneously jump to the lower level emitting radiation, then these photons can go in any direction they like. They can have any polarization they like. But in the case of stimulated emission, which is this figure over here, the stimulated emission takes place in the same direction. It is at the same frequency as the incident radiation. It is the same polarization as the incident photon. Therefore, the emitted radiation, the stimulated radiation, is coherent with the photon that stimulated the emission. So, a laser or a maser is very, very special because the radiation is dominated by stimulated emission rather than spontaneous emission. We will discuss this at great length. And this radiation is coherent. It is in a particular direction, it's at a particular frequency, it has a particular polarization. That's what makes radiation from a laser or a maser so unique. Now, let us define the absorption and emission coefficients J nu and alpha nu in terms of Einstein's A and B coefficients. We already said B is equal to C, so we are only dealing with two coefficients A and B. Now, if you go back to the second lecture, I defined the emission coefficient J nu as the amount of energy emitted in a volume dV going into a solid angle d omega in a frequency range d nu in a time dt. So that proportionality is the emission coefficient. Now, since each atom contributes an energy h nu in each jump or each transition, and this goes into a solid angle d omega, the above energy, this expression for the energy, can also be written as h nu over 4 pi solid angle going into solid angle d omega multiplied by N2 into A21, where N2 is the number of atoms in the upper level 2 and A21 is the Einstein coefficient for spontaneous emission from level 2 to level 1. So that is the relation between Einstein's coefficient A and what we introduced in the second lecture as the emission coefficient of a macroscopic body, that is determined by spontaneous emission coefficient, Einstein coefficient A. Similarly, so the emission coefficient J nu is related to Einstein coefficient A. Similarly, the absorption coefficient, if you recall the definition of absorption coefficient, we defined the specific intensity I nu, and we said if there is an absorber over a length ds, a fraction of alpha of the incident specific intensity is eaten away. Di therefore is equal to minus alpha I nu ds. So that is how we define the absorption coefficient alpha nu. We didn't say why there was absorption. Classically, we didn't know. And what is the origin of the absorption, how to calculate the absorption coefficient. None of these things were clear then. So now we are making the first step towards it. Now it's very easy to show, just like in the previous slide, that the absorption coefficient alpha nu that we introduced before is related to Einstein's coefficient B, B12, which is the transition from 1 to 2, which is equal to the coefficient B21, which is the transition from 2 to 1. Remember, both are induced by the incident radiation. One is stimulated absorption, the other is stimulated emission. So the absorption coefficient is related to Einstein's B coefficient. Now, this absorption coefficient is uncorrected for stimulated emission. What I mean is the following. There are 17 atoms in the ground state, and there are 3 in the upper states. There are incident photons, 17 incident photons. And so these 17 atoms in the ground state make a transition to the upper state. So you will say the net absorption is 17 photons have been absorbed. But in the meantime, the 3 which were already sitting in the upper level could also jump, stimulated by the external electromagnetic field. So if all 3 jump down, the net absorption is not 17, but only 14. Therefore, the real absorption coefficient has to be corrected for stimulated emission. So this is the absorption coefficient for stimulated emission, stimulated absorption, which is uncorrected for stimulated emission. Before Einstein 1917, there was no stimulated emission, and therefore there was no correction needed. So we have to correct this. It is useful to regard stimulated emission as negative absorption. Absorption is going from lower level to upper level. So instead of saying the stimulated emission is jumping from level 2 to 1, let's call it negative absorption, because it is the reverse of absorption. Please remember that stimulated emission and stimulated absorption are both proportional to the incident radiation field at the frequency nu. Experimentally, you cannot separate stimulated absorption and stimulated emission. Both are taking place simultaneously. Therefore, it makes a lot of sense to define a net absorption coefficient which takes into account not only stimulated absorption but minus stimulated emission. Therefore, the absorption coefficient corrected for stimulated emission is alpha nu is equal to h nu over 4 pi plus N1 B12, which is stimulated absorption going from level 1 to 2, minus N2 B21, which is stimulated emission jumping from level 2 to 1. This is stimulated absorption and this is stimulated emission. So that's getting interesting. So now this is the same formula as in the previous slide. Since B12 is equal to B21 by symmetry, alpha nu is h nu over 4 pi N1, the number in the lower level, multiplied by B12, multiplied by square bracket 1 minus N2 divided by N1, where N is the number of atoms or molecules in level 2 divided by number in level 1. Now, in thermal emission, when matter is in thermal equilibrium, you know from Boltzmann statistic, the ratio of the population in the upper level to the lower level is given by e to the power minus the energy level difference, which is equal to e to the power minus h nu over kT. At any finite temperature, this quantity on the right-hand side is less than 1. Therefore, the number in the lower state is always larger than the number in the upper state. Therefore, alpha nu, the absorption coefficient corrected for stimulated emission, can be written like this. And the second term, which I'm pointing to with my cursor, is stimulated emission. And the first term is stimulated absorption. And there is a minus sign in between because this is absorption and that is emission. So plus minus gives me the net absorption coefficient. Now, as I said, under normal circumstances, when matter is in thermal equilibrium, N2 over N1 is always less than 1. In other words, as you go to higher and higher levels, the number is always decreasing. It's decreasing exponentially. by the Boltzmann factor e to the power minus h nu over kT. But under some special circumstances, the number in the upper level can be larger, indeed very much larger, than the number in the lower level. N2 can be greater than N1. In this case, the absorption coefficient is negative, because we said the absorption coefficient is the sum of stimulated absorption minus stimulated emission. When the number in the upper level far exceeds the number in the lower level, the second term, which is a minus sign, becomes larger, therefore the absorption coefficient becomes negative. Because N2 now is much larger than N1, the absorption coefficient becomes negative. If matter is in thermal equilibrium, N2 over N1 is always less than 1, absorption coefficient is always positive, and there is always attenuation of radiation. If you go back to lecture 2, you may remember that I said when there is population inversion, something dramatic can happen. You have negative absorption coefficient. And if you remember way back from second lecture, I introduced the notion of optical depth tau. Optical depth tau was the integral of the absorption coefficient alpha over the path length. So it is the net absorption over a certain path length. Now, so that's what optical depth is. So if absorption coefficient is negative, the optical depth is negative. Previously, we said the intensity of radiation will be the intensity of radiation you will get from a black body at that frequency multiplied by e to the power minus tau. And tau was a positive number. Now tau is a negative number. So it is exponential to the power plus modulus of tau. Therefore, if you have a negative optical depth, which is a modus 100, I will have an amplification of the intensity by e to the power 100, which is 10 to the power 43. So that's what a laser or a maser is. In a laser or a maser, you arrange it so that matter is not in thermal equilibrium and there is extreme population inversion. The number of atoms or molecules in the upper level far exceeds the number in the lower level. This makes the net absorption coefficient negative. The optical depth is negative. Therefore, there is not absorption but amplification of radiation by stimulated emission of radiation. So that's where the name laser or a maser comes from. Light amplification by stimulated emission. When Einstein formulated his quantum theory of radiation in 1917, there was no way to calculate the coefficients A and B. He simply said there's got to be this, and this has got to be the relation between A, B, and C. Now, to actually calculate this coefficient A and B, which are transition probabilities from level 1 to level 2, level 2 to level 1, one had to wait for the full quantum mechanics. And the first person to calculate these from first principles was Enrico Fermi, the great Enrico Fermi, in a classic paper in 1932. Now, this paper was a semi-classical theory. Fermi treated matter quantum mechanically because Einstein and Bohr had taught us how to deal with energy level. But he treated radiation still classically using Maxwell's theory. From quantum mechanics, Fermi was able to derive that the coefficient B is related to what is known as matrix element in quantum mechanics. When you learn quantum mechanics, you will recognize this object xmn. It is the transition probability of the dipole moment, E times x. My cursor always disappears. E times x is dipole moment. So it is the transition, it is the matrix element of the dipole moment between level 2 and level 1, or level m and level n. And of course, A and B are related, just as Einstein said they ought to be related. Now, for a complete treatment where both matter and radiation are treated quantum mechanically, one had to wait till around 1948 or so, when the quantum theory of radiation was formulated by Feynman, Tomonaga, and Schwinger, for which they were awarded the Nobel Prize. This is, of course, the theory of quantum electrodynamics, the most successful theory in quantum physics, often referred to as the jewel of physics. But we won't digress into that. All I'm saying is now we have a full quantum theory of matter and radiation. So we can calculate from first principles the emission coefficient, and absorption coefficient from first principles. Now let us discuss two-level systems in quantum mechanics. Now what I'm going to describe now is taken largely from chapter 9 of volume 3 of Feynman lectures. I shall ask Dr. Susan Conard to give a reference to this in this lecture. If you don't own a copy of Feynman's volume 3, you can click on that link and you will be able to have a ready reference. Apart from hydrogen atom, the two-level system in quantum mechanics is the simplest and the cleanest system. So if you want to learn quantum mechanics, please work through this algebra, keeping beside you chapter 9 of volume 3 of Feynman lectures. So let's go. Let's consider the first two-level system, which I've already introduced to you, a magnetic moment mu in the presence of an external magnetic field H. The energy of interaction E is given by minus mu dot H. So where the magnetic moment itself is given by minus G, the G factor, Bohr magneton multiplied by the angular momentum J. If you remember, we discussed all this when we discussed 21 centimeter radiation. For a single spin, an electron or a proton, G is 2, and the total angular momentum is just the spin angular momentum S. Therefore, the energy of interaction, which is minus mu dot H, is given by this formula, where this quantum number ms can take the value either plus 1/2 or minus 1/2, and the energy E is split into two levels, plus mu bh and minus mu bh, which is shown over there. So energy level E of a magnetic moment mu in the presence of an external magnetic field H is split into two levels. The upper level corresponds to the spin angular momentum of the particle being parallel to the magnetic field, and the lower level corresponds to the spin angular momentum being anti-parallel to the external magnetic field. That energy level difference is given by 2 times mu b times h, and that just comes from this formula. Plus mu bh minus mu bh, and you will get 2 mu bh. So that's the simplest two-level system that you're familiar with already. But you're familiar with one more two-level system which I introduced, which is the hyperfine structure of energy levels. Now, the energy levels that Niels Bohr derived for the hydrogen atom in 1913 were characterized by a single quantum number, the principal quantum number n, 1, 2, 3, and so on. These are the Rydberg levels. But the interaction between the spin angular momentum, about which Niels Bohr did not know in 1913, and the orbital angular momentum L, splits the energy levels, and that is known as the fine structure. But we won't discuss the fine structure now. Let us straight away jump to the hyperfine splitting of the energy levels. In particular, the hyperfine splitting of the ground state of the hydrogen atom, which is n equal to 1 level of the hydrogen atom, which has an energy of minus 13.6 electron volts. That, I argued, will be split into two levels, which correspond to the following. Both electron and proton have spin angular momentum half h bar, This is the proton, these are the electrons. The electron. The upper level corresponds to proton and electron spin angular momentum being parallel. The lower state corresponds to them being anti-parallel, just as in the Zeeman formula that I showed before. The magnetic interaction between the proton and the electron, two bar magnets. Previously you had one bar magnet and an external magnet. Now you have one bar magnet and another bar magnet corresponding to the two elementary particles. The magnetic interaction between the two splits the two levels. And Fermi, once again, was the first person to calculate this hyperfine splitting, and he showed that this energy level difference is given by this simple formula where psi squared 0 is the probability that the electron in the oneness level of the hydrogen atom can actually be found at the nucleus, R is equal to 0. It's a very remarkable property of the oneness state of the hydrogen atom that although it is far, far away from the nucleus, such a distance of 10 to the power minus 8 centimeters, whereas the nucleus is 10 to the power minus 13 centimeters, quantum mechanics tells you that the oneness state has a finite probability of being at the nucleus. And that is the magnetic interaction between the oneness electron and the spin of the proton, which causes this hyperfine splitting. And you know that that wavelength corresponds to 21 centimeter. We discussed that at great length. It's profound importance in astronomy. And its frequency was 1420 megahertz. I told you that this frequency is known far more accurately. Here it is in all its glory. Till quite recently, this frequency was used to define the unit of time, to define the second itself. Today it is defined in terms of a similar frequency from the cesium atom, whose frequency is known even more precisely than this. So this is the second two-level system in quantum mechanics. If you remember this particular quantum number, the spontaneous transition probability A21 of a hydrogen atom jumping from this upper hyperfine level to lower hyperfine level is incredibly small, and the lifetime of this upper level is about 10 million years. We discussed this when we discussed the interstellar medium. That long lifetime is now going to be put to use in making a mason. The third two-level system in quantum mechanics is the ammonia molecule. This discussion is taken from Feynman lectures. So here is an ammonia molecule, 3 hydrogen atoms and a nitrogen atom. They form a tetrahedron. Now, the ammonia molecule has many degrees of freedom, translational degrees of freedom, rotational degrees of freedom about many axes. This is not a simple diatomic molecule. It has many vibrational modes and so on. In particular, there are 2 configurations of the ammonia molecule which concern us. This nitrogen atom can be either above the plane defined by the 3 hydrogen atoms, or it can be below the plane defined by the 3 hydrogen atoms. These 2 configurations are, of course, geometrically precisely symmetrical with one another, and in classical physics, if you could discuss molecules in classical physics, these 2 configurations will have the same energy. So, here it is. Here is the potential energy curve of one of the configurations of ammonia molecule. Let us say the nitrogen atom is above the plane of the hydrogen atoms, and this is the nitrogen atom is below the plane defined by the 3 hydrogen atoms. And there is a huge potential barrier between these two configurations. But in quantum mechanics, even though there is a potential barrier, a nitrogen atom from this potential minimum can tunnel its way quantum mechanically to this. Similarly, this nitrogen atom can quantum mechanically tunnel over here. So we have discussed quantum mechanical tunneling when we discuss fusion in the sun. This is the same quantum mechanical tunneling. And what this tunneling probability does is to make these two energy levels split again. Therefore, these two configurations, in the absence of quantum mechanical tunneling, will have the same energy. E1, let us say this is E1, let us say this is E2, will be equal to E. But the tunneling between these two minima splits the energy levels. And again, you have a two-state quantum mechanical system with different energies. And those energies are E1 and E2. They are no longer equal because quantum mechanical tunneling has split it. Just as before energy level E became E plus mu B and E minus mu B, similarly you will have the energy level E1 will be E plus some A and E minus some A, where A is to be derived from quantum mechanical tunneling. Now, a real ammonia molecule can either be in the state 1 or state 2, and quantum mechanics tells you that it can be in both states. So the ammonia molecule's actual state will be an admixture of ammonia molecule in state 1 and ammonia molecule in state 2. So the amplitude or the wave function of the ammonia molecule will be a sum of two terms. One is the amplitude that the ammonia molecule will be in state 1 with the coefficient C1, and the wave function of the ammonia molecule in state 2 with an amplitude C2. The amplitude C1 and C2 will vary with time because the molecule is jumping between the two states. If at time t equal to 0, the molecules was in state 1, then at a later time it could be in state 2 and it could oscillate. Remember when we discussed neutrino oscillations, this is what we discussed. And that's what I mean. If you now go back and read this chapter 9 of Feynman Lectures, volume 3, you will have an excellent introduction to pure states and mixed states and oscillating probabilities. So let us say that at time t equal to 0, the ammonia molecule was in the upper state C, therefore the amplitude C1 is equal to 1, the amplitude C2 is equal to 0. But amplitude C1 and C2 vary with time, as e to the power I times Et over h bar multiplied by cos At over h bar and sine At over h bar. So both these amplitudes are time varying. One varies as the cos and one varies as the sine. So the probability of finding an ammonia molecule in state 2 is related to the square of the amplitude C1 and C2 squared. So the probability of finding the ammonia molecule in state 1 will be C1 squared, which will be proportional, which will be equal to cos squared At over h bar, and the probability of finding it in the level 2 will be equal to sine squared At over h bar. Now you can plot the probability of finding the ammonia molecule in state 1 and state 2. One will be square of the cosine and one will be the square of the sine. They will be precisely as shown in this diagram. So the probability of finding the ammonia molecule in level 1 and 2 will oscillate as shown here. Now, it turns out because nitrogen is heavier than 3 hydrogen atoms, the center of mass of the ammonia molecule is somewhere there, between closer to the nitrogen than to the hydrogen. Now, as is beautifully explained in Feynman Lectures, this gives rise to an ammonia molecule acquiring a permanent electric dipole moment. Let me repeat, this comes because the center of mass is closer to the nitrogen than the 3 hydrogen. This results in net charges, which is a dipole moment. And the dipole moment, let's call it mu. The energy of interaction between the dipole moment and an external electric field will be minus mu dot E, just as the energy of a magnetic moment in a magnetic field is minus mu dot H. Here it will be minus mu dot E. Okay, now things are getting interesting. So here are the 2 configurations. Here is an external electric field, and the dipole moment of the ammonia molecule can either be in that configuration or in that configuration, corresponds to the nitrogen being above the plane or below the plane. And if there was no quantum mechanical tunneling, the energies E1 and E2 will be equal to just E0. And therefore, what this dipole moment does is to add an energy plus mu E, subtract an energy minus mu E. But please remember that this formula that I have written simply to recall what we wrote in Zeeman splitting cannot be correct, because the energy levels E1 and E2 are not equal anymore. They are E plus A and E minus A. So you have to solve this problem in an honest manner, and it's a very simple problem to solve. And I suggest you work through the algebra, keeping Feynman lectures next to you. Now, when a molecule flips from state 1 to state 2, nitrogen is above the plane, nitrogen is below the plane, the dipole moment flips, and therefore these 2 configurations have different energies in an external electric field, because the dipole moment splits. The dipole moment is always pointing from the center of mass towards the plane, center of mass towards the plane. Therefore, the dipole moment flips. Now, if you solve this very simple problem, this is as simple a problem as it will get in quantum mechanics, then the energy levels E1 and E2 of the ammonia molecule with the nitrogen above and nitrogen below the plane in the presence of an external electric field is given by this expression and this expression, and the square root can be expanded because in a real experiment the electric fields are so small that the splitting due to the electric field mu E is very small compared to the splitting due to quantum mechanical tunneling between these 2 states. And therefore, I can take A outside, A squared outside, and I'll get A, and then I'll get square root of 1 plus mu squared E squared divided by A squared. I can expand that and keep only the first term, and I will have these 2 expressions over there. So energy E1 will be proportional to the square of the electric field. Energy E2 will be proportional to the square of the electric field. This has a plus sign and this has a minus sign. And that is what is important for our discussion now. So plotted as a graph, what I've shown here are the 2 energy levels, E0 split into E0 plus A and E0 minus A due to quantum mechanical tunneling. There is no electric field. If I now apply an electric field, these 2 levels will increase as given by this expression, E0 plus square root of A squared plus mu squared E squared, where mu is the dipole moment and curly E is the external electric field. Very good. So now we have 3 2-level systems. One is, of course, the Zeeman splitting. We'll leave that aside. One is the hyperfine splitting of the ground state of the hydrogen atom. And the other is the 2-level system which corresponds to the ammonia molecule. So now we can go back to Einstein 1917 and create a situation where you have an inverted population, stimulate these atoms and molecules to jump coherently from the upper level to the lower level, and you will have either a laser or a maser. So please permit me some 5 minutes or so more to explain to you how a maser is actually made. To make a maser or a laser, we need to create an inverted population where the number of atoms or molecules in the upper state far exceeds the number in the lower state. This is done as follows. One can make an experimental setup using which we can prepare the atom or molecule such that they're all in the upper state. You tailor make it in that fashion. In the case of ammonia molecule, we can pass a beam of ammonia molecules through a region of inhomogeneous electric field. Why? Because in the presence of an external electric field, the two levels corresponding to the nitrogen being above and below are given by these two expressions. One is plus E squared and one is minus E squared. So if I can create an experimental situation where there is a gradient of the square of the electric field, then it will either favor this state or it will favor this state. So how do I do that? I have a beam of ammonia molecule going through a few slits. So it is collimated beam of ammonia molecules. It is a mixture of ammonia molecules in the two states 1 and 2. I apply perpendicular to the beam an electric field whose gradient of the square of the electric field increases there. This arrow represents the arrow does not represent the direction of E. It represents increasing E squared. Why E squared? Because these two energies are proportional to plus E squared and minus E squared. So let's try to understand this. So this is the same picture as before. A beam of ammonia molecule passes through a region where there is an inhomogeneous electric field. The electric field is not uniform. There is a gradient of the electric field and there is a gradient of the square of the electric field. Now suitable electrodes are used. So if you use a parallel plate capacitor to create the electric field, you will have a uniform electric field. That's not what you want. So you probably need a pin and some horribly complicated electrode to create an inhomogeneous electric field to set up a gradient of E squared in this direction. But experimentalists are very clever. They can do these things. So let us now consider the upper state E1. Its energy is proportional to E0 plus A plus E squared. So the upper state will prefer smaller E squared because there is a plus sign. It will prefer this third term to be as small as possible. So it will prefer a region where the square of the electric field is small. Now let's look at the lower level. Its energy is also proportional to E squared, but it is proportional to minus E squared. Therefore, the lower level will prefer a region of higher E squared. Larger the E squared, because of the minus sign, it will have lower energy. So that is the clever thing that Charlie Townes and his collaborators did by creating a gradient of the square of the electric field. So in the upper beam, so this beam will split into two beams. In the upper beam, the molecules will be in the lower state. Why? Because the upper beam, E squared is larger. E squared larger means it will be in the lower state. In the lower beam, which is over there, the molecules will be in the upper state. Why? Because E squared is smaller, and that's what upper state will prefer because there is a plus sign there and not a minus sign. So I have created a filter. The upper beam is purely lower state and the lower beam is purely upper state. Now, so I have created an inverted population and I take this beam which consists of ammonia molecules, all of them in the upper state, and make them enter a resonant cavity in which there is a frequency omega naught in that direction. What is that frequency omega naught? That frequency corresponds precisely to the energy level difference between the two states of the ammonia molecule. And that frequency happens to be 24 gigahertz. So these molecules in the upper state, when they enter this cavity, resonant cavity, are irradiated by an electromagnetic radiation at a frequency of 24 gigahertz, which corresponds to the energy level difference between the upper state and the lower state. All the molecules in the upper state will jump coherently to the lower state. They will jump coherently into the lower state. Therefore, the molecular energy in the upper state has been converted to electrical energy. In other words, the electromagnetic energy in this cavity has now been amplified by stimulated emission of ammonia molecules jumping coherently from the upper level to the lower level. In the case of the hyperfine splitting of the ground state of the hydrogen atom, the beam is made to pass through an inhomogeneous magnetic field. That's because the splitting is related to the magnetic field. So you have two magnets of some complicated geometry so that you create a gradient of the magnetic field and thereby split the beam into the upper state and the lower state. Now, after selecting the atoms or molecules in the upper state, they are collected or trapped in a cavity. And we will have an extreme case of inverted population. All the molecules are in the upper state. All the atoms are in the upper state. Now, in the cavity, it is subjected to an oscillating electric field, an external electric field with a frequency of oscillation equal to the energy level difference between the upper state and the lower state. There will be stimulated emission and the radiation will be coherent, and thus the energy in the oscillating field has been greatly amplified. Now, let's repeat this, summarize it. All the molecules that enter into this cavity are in the upper state. There is an oscillating electric field inside the cavity. The frequency corresponds to E1 minus E2. The probability of finding the molecule in state 1 will oscillate, as shown in this diagram. But what you do is you adjust the length. Molecules are coming with a certain velocity. You adjust the length of the cavity such that when they enter, they are in state 1, and when they exit, they are in state 2, because the transition probability from level 1 to level 2 is a function of time, and I can translate this axis from time axis to a distance because I know the velocity of the beam. Thus, there will be a coherent dumping of energy into the cavity, and the radiation of the oscillating electric field in the cavity will now be greatly amplified. And we have a measure. Microwave because this is 24 gigahertz. Microwave amplification by stimulated emission of radiation. Now, the idea of such an amplification was first advanced in 1952 by two Russian physicists, Basov and Prokhorov, in 1952. In 1953, Charles Townes and Gordon and Ziegler in Columbia University in New York made the first ammonia measure. And in 1964, Basov, Prokhorov, and Townes were awarded the Nobel Prize for this monumental discovery, for fundamental work in the field of quantum electronics, which has led to the construction of oscillators and amplifiers based on the Maser-Laser principle. Only the Maser was made in 1953. The hydrogen Maser was made in 1964 by Norman Ramsey at Harvard University. As I said, till quite recently, this defined the standard of time, no longer. A laser is light amplification of stimulated emission of radiation. Arthur Shallow and Charlie Towns wrote a very famous paper in 1958 where they gave details with drawings of how to make an amplifier in visible light, a laser. They didn't make the laser, but they spelled out exactly how it can be made. The first laser was made by Theodore Maiman in 1960. It was a ruby laser. It was a pulsed laser. It was a solid-state laser. Now, if you don't have a unique system like an ammonia molecule or the hyperfine level of hydrogen atom, what you do is to use a three-level system. You have a ground state, an excited state. In between, you have an intermediate state, which is metastable. That means it has a very long lifetime. So you excite an atom or a molecule from the ground state to an excited state, and it jumps to the metastable state because the lifetime of that is very large. All the atoms and molecules accumulate in this metastable state. Then you tickle it with an external radiation, and bingo, they all jump down, and you have a laser. So in the case of the hydrogen laser, you didn't need a three-level system because the upper level has a very long lifetime of 10 million years. But in other atoms, if you want to make a helium neon laser or an argon laser or a mercury laser or a carbon monoxide laser, you have to use a three-state systems. Now, finally, I come to what I want to talk about. I have far exceeded 1 hour, but please bear with me. The first celestial maser was discovered in 1965, just a year after the first laser was made, and that was the OH maser. This was followed by water vapor maser in 1969. Since then, many more masers have been discovered. Here is a list of masers, which includes ammonia, formaldehyde, water, silicon monoxide, and so on. These are all masers in the interstellar space. Now, the astrophysical conditions needed for masing is there must be a pump. You have to create population inversion. So there must be a radiation field which excites the molecules to the upper level. And you must be able to create an inverted population. Here we did this by passing it through an inhomogeneous electric field or inhomogeneous magnetic field. But in interstellar space, you don't have all that. But somehow you have to create an inverted population. Secondly, unlike in terrestrial lasers and masers where you have a cavity in which you make things bounce back and forth, in the case of lasers you have two mirrors and the beam bounces back and forth millions and millions of times, and thereby you get amplification. In an astrophysical situation, there are no cavities, there are no mirrors, so it's a single path propagation. So clearly, you need to have negative absorption coefficient, resulting in a large negative optical depth, all in a single path. And you also need velocity coherence, because if the molecules are all moving at different velocities due to Doppler effect, the frequency that you will need to pump it from level 1 to level 2 will be different by Doppler shifting. So you can't have that. So you need velocity coherence along the path length. And of course, one needs high resolution interferometry to detect them, but that's a separate story. So, but there's a tall orders here. You need velocity coherence, you have to create a negative optical depth, a large negative optical depth, and so on. And you don't have clever experimental physicists to do so. That's the beauty of nature. Nature manages to do all these things. These lasers and interstellar masers will obviously be beamed just as terrestrial masers and lasers are beamed in the forward direction. They will also be rapidly variable, since the gain depends exponentially on population inversion. So you may have situation of population inversion, that you must lose this condition of population inversion. Therefore, a measured source may be flickering. So you have to cope with this dramatic variability in intensity. But once you detect it, it will be incredibly intense. And how do you know that it's a maser or laser line? It will have a very sharp frequency profile, and it will have a very high brightness temperature. Go back to lecture 2 and also my lecture on pulsars. If you have coherent radiation, you will have very high brightness temperature because the optical depth is negative. Now, what are the astrophysical sources where you find masers? Believe it or not, a very large number of sources. Comets, for example. In many comets, ammonia masers, methane maser, hydroxide masers have been seen. Planetary atmospheres, like atmosphere of Jupiter, shows cyclotron masers. Stellar atmospheres, red supergiants, have a lot of dust in the outer layers. There is a lot of infrared radiation. You have pumping radiation. So you have silicon monoxide masers in the outer layers of red supergiant stars. Star-forming regions where there is a molecular cloud being hit by a supernova blast wave, you have ideal condition for maser. And very often you have OS maser, methanol maser, and water vapor masers. And then, of course, you have mega masers in extragalactic sources, water, hydroxyl, formaldehyde, and so on, have been seen in accretion disks around supermassive black holes. So if you have a molecular cloud, which is being clobbered by a supernova blast wave, which we discussed in one of the earlier lectures, then in the shocked cloud, which has been overtaken by the shock, you have OH masers. This is routinely seen. These OH masers correspond to some transition. We won't deal with that. A very sharp line. Look at how sharp these lines are. That is how we identify it as an amazing line. And then, of course, if you now calculate what should be the temperature of a hypothetical black body, which will emit that much intensity at that frequency, that will correspond to some 10 to the power 30 Kelvin, very high brightness temperature. This is the water vapor maser in Orion Nebula. And here in the galaxy, NGC 4258, there is a supermassive black hole over there, and this is the accretion disk, and you have a very large number of water vapor masers in this. All these dots are masers. These dots are red-shifted frequency. These are blue-shifted. That means the accretion disk is rotating. One set of masers are moving away from you. Other set of masers are coming towards you. Now, because these masing lines have very sharp frequency, one has been able to determine the velocity of the rotation very precisely, and that follows Keplerian law. We discussed that when we discuss, or we will discuss that when we discuss supermassive black holes. In 1994, planet Jupiter was clobbered by a comet. The comet was known as Schumacher-Levy. And here is the comet hitting planet Jupiter. And when it hit it, the impact created water vapor maser at 24 gigahertz. Now, this is a terribly exciting thing. Now we have 5,000 exoplanets, about which I will discuss in the next lecture. And one possible way of identifying exoplanets may be if they are struck by a comet in the stellar system, then there may be maser emission. If by luck it is beamed towards you, you can detect this maser emission, and then you will have an excellent candidate for an exoplanet. So this is a very exciting possibility of comets impacting on planets, triggering water vapor masers. So I apologize that I went on long, but I didn't want to split this into 2 lectures. This is an extremely important subject, particularly in view of the excitement in exoplanet research. In the next lecture, we will go on to discuss exoplanet, undoubtedly the most exciting frontier in astronomy today. Till then, thank you very much for your attention.